In this video, we're going to talk about differential rate laws. Now, before we get too far into this video, I want us to do a quick math review. Why? In order to answer and solve some of these differential rate law problems, we're going to need to work with logarithms, more than just simply taking the log in your calculator. What do I mean by that? Well, if we have log of x raised to the y, what does that equal? Well, you can take this y and move it down in front to make it be y log of x. Those are algebraically the same expression. Alternatively, if you have log of x minus log of y, that equals the log of x over y, where whichever one was being subtracted goes on the bottom of the expression. They are the same thing algebraically. Another rule that you may not remember is if you have x raised to the m over y raised to the m, that's the same thing as x over y both raised to the m. These are all the exact same expression. All right, let's do an example. Let's say we have 2x equals 8. How do we solve for x? Well, you may just say, well, that's x equals 3, because 2 raised to the third equals 8. 2 times 2 is 4 times 2 is 8. But how did we get there? What we could have done is taken the log of both sides, meaning the log of 2 raised to the x equals the log of 8. Now, what did that do for us? Well, if we use this expression right here, what that says, if we got log of 2x, that's the same thing as x times the log of 2. So let's write that here. X log of 2 equals the log of 8. All right, once again, how does that help us? Well, now we can divide both sides by the log of 2, canceling out the log of 2 here and leaving us with the log of 2 on this side. And now we can simply place this into our calculator, where we type in the log of 8 divided by the log of 2, and that would give us x equal to 3. It's really easy when it's something like this, where you can solve this in your head, but whenever x is equal to something besides a whole number or a very easy to see number, this way of completing this expression is going to be more efficient. So keeping in mind these log rules, I find to be very helpful. Okay, so now on to differential rate laws. Differential rate laws is just simply a function for the rate of change in concentration. Now, if you remember back to the initial rate laws, we had the change in concentration over the change in time. These do not have time as part of the function. We are going to look at integrated rate laws later, and so these words differential and integrated, you should remember those words from calculus or pre-calculus. But how we're going to utilize them is just differential rate laws are simply a function of the rate of change in concentration. So notice how all of these have rate equals K, where K is just a constant, times the concentration of that change in concentration, okay? And then they're raised to some kind of exponent. And the exponent is going to tell you the order of the reaction. Now, what do I mean by that? So notice down here, your 0. That 0, anything raised to a 0 is 1. That's why this is k times 1. Okay, so it's sort of like saying k times 1, where this part of the expression is equal to 1, because anything raised to the 0 is 1. So this is 0 order because all of my concentrations have a 0 exponent, and so this is a 0 order reaction. First order means that I have one concentration that is raised to the first. A second order reaction can either be a 1 concentration raised to the first and another concentration raised to the first, or it can be 1 concentration raised to the second, but the sum total of all exponents needs to equal 2 for a second order. Similarly, a third order reaction would mean you have either 1 that is raised to the third, or you could have 3 things raised to the first, or you could have 1 thing raised to the second and another thing raised to the first. It doesn't matter. But this first, second, or third order is just simply going to allow you to check and see, hey, what's the rate of change of my substance that I'm looking at as a function? Okay, and so my rate is equal to that function. Obviously, things that are raised to the first order are changing more than things to the zero and changing less quickly than things raised to the second. Okay, but do notice that time is not a function. Whenever we integrate these differential rate laws, that will allow us to make time part of this function. Another thing to note is that the order of a reaction can only, okay, I'm going to tell you this 100 times, be found experimentally. I will often see people say, oh, well, this has a 1 as a coefficient, this has a 2 in front of it. Doesn't that therefore mean it's first order with regards to A and second order in regards to B? No, never. You cannot find reaction order from the stoichiometric coefficients. You can't. It can only be found experimentally. So whenever I ask you, find the order of a reaction, you're going to have to find that algebraically. And we'll talk about how you do that in a minute. But you're going to algebraically find reaction order via experimental data. So whenever I ask you to find the general form for a rate law, a differential rate law, all that means is you write down rate equals K, and then your concentration of, and A is a reactant, B is a reactant, you don't include your C or your D, and then you raise it to whatever power you are using and you are finding experimentally. So the general form is rate equals K times concentration raised to an exponent times the other reactant raised to the exponent, and so on and so forth. If it is zero order, it's just zero, or it can be first, second, third, and so on. But that is the general form, just means write rate equals K times and then all of the different reactants in brackets with a order on top. All right, so let's look a little bit further then. Let's look at K. So K is a constant, and so once again you find that experimentally, but your K's units are going to depend upon the reaction order. What in the world do I mean by that? Well, let's look a little further. So if rate is equal to your concentration per time, so rate equals molarity times time. For a zero order reaction, my rate on this side should be molarity per second, and my K, what units do I need to have in order to make them be molarity per second? This is to the zero power, and so that means that this one is not going to have any units, so it's just 1, which means my rate constant needs to be molarity per second in order to make the units on both sides of the equal sign be the same. Let's work this for rate of first order. So we've got molarity per second is rate on this side. My units for K, I need to determine them. But K is times something raised to the first power. That something is concentration, so that's molarity to the first power. Which means the units that I need for my K need to be 1 per second in order to have the same units on both sides of the equation. Because if it's 1 over second times a molarity, that means this whole side is m over s, which is what I need it to be to match my rate units. What about second order? Let's try that one. Molarity per second equals something, some units for K, times some m concentration for A, times some m concentration for B. So if I just have it be, for instance, 1 over second, that would mean I have molarity squared on top per second. I need to get rid of another m. So to do that, I put it on bottom, because now your 1m on top is going to cancel with 1m on the bottom, leaving me with molarity per second, which matches my units for my reaction rate. And so your K's units are just simply going to depend upon reaction order. Let's work a couple of types of questions. This first question is going to depend more on the initial rates, and that is what we talked about in the prior video, where we see the reactants decrease over time while the products increase over time. And so that's what this type of question is. And so it says, in a certain experiment, over a specific time period, 0.0048 moles is consumed in a 2-liter container each second of reaction. What are the rates of production of P4 and H2 in the experiment? So the first thing we need to figure out is, what is our rate for our pH3? So how quickly is it disappearing? Well, we have 0.0048 moles per 2 liters, and so that equals 0.0024 molar. And I should write out MOL. So if that's molarity, that's my concentration, but that was per second of reaction. So this right here is my rate, because remember from before, my rate is my change in concentration with my change in time. And so that's in this form, molarity per second. And so now I can take that and fill it in here as my rate. And then this coefficient, this is our general equation. The idea that the rates are proportional to the coefficients for these initial rate problems, not for my differential rate laws, but for my initial rate problems. And so I can write this out as my rate of pH 3, 0.0024 molarity times second inverse, so per second, times the rate of P4. And I don't know the rate of P4 yet. And then we'll set it equal to my coefficient of pH 3, which is 4, over my coefficient of P4, which is 1. And so if I perform some algebra and solve for x, I'm going to end up with my rate of P4, which is what my x is equal to, equals 0.0006 molarity per second. Now, does that make sense? If I've got my reactant, which is pH 3, and there's 4 of them, for every 4 that decompose, I'm going to create only 1 of my P4s. And so you would expect it to be going at basically 1/4 the rate of pH 3. 1/4. Okay, and so this is my rate here of my P4. But what about the second one? Can we perform the same one to figure out our hydrogen rate? Absolutely. So please stop the video at this moment and try and solve for the rate of hydrogen in this experiment. So you should have used an equation like this where we have our rate of pH 3, which is the same as before, 0.0024 molarity per second over my rate of H2 equals my coefficients, and we end up with x having a rate equal to 0.0036 molarity per second. And so these are my rates, but these are kind of based upon those initial rates. And so I wanted to remind you of these, work a little bit of math, but that way you can differentiate them in your mind from those questions that are our differential rate laws. And so these are your initial rate type problems. The next question is a differential rate law problem. So we have a reaction, and this reaction was studied at 25 degrees Celsius. Really, the temperature is irrelevant except for it's telling you under what conditions the rate laws are going to be applicable. Because if you increase the temperature of a reaction, you're going to increase the number of collisions because those molecules are moving faster. And so your rate is directly dependent upon the temperature by which the experimental results are carried out. And so that's all it's doing, is it's establishing what are the parameters of the experiment. That is all. So these results were obtained, and we're going to try and do two things. Number one, determine the rate law, and B, calculate the value for the rate constant for each experiment, and then an average value for the rate constant. And so remember from before, we can have some reaction order. And so we have rate equals K times some concentration raised to some exponent, some other concentration raised to some other exponent. In this example, it's second order because we have a 1 and a 1, and 1 plus 2 is equal to 2. So it is second order. But we don't know. Is it 2, 1? Nope. Remember, experimental data only, so you cannot use those stoichiometric coefficients. Instead, we need to base what is our rate law off of our data that we collected experimentally. And so you'll be given a table like this. And so that's one way you can tell if it's differential, is if you have some concentrations and then some initial rates. And those initial rates are simply these rates that are listed in your differential rate laws. So your differential rate laws are dependent upon your initial rates. Let's work this problem and see how we might do that. So here's the same table, I just moved it so I can have a little more room to write. Now, I wrote the general form for our rate law here. Rate, which is our initial rates, equals our K, which is our constant, times the concentration of I, so that's our first reactant, raised to M. M is just an exponent. It's a placeholder. Some numerical value is going to go there. It might be 0, 1, 2, 3, etc. They're going to be integers. Okay. Obviously, with experimental data, you may have to round your integer, but they're supposed to be integers. And then here our other reactant, raised to n, which just means that's a placeholder for whatever the exponent is. This is our rate law. What do we do with it? We are going to do a whole bunch of math. And so this is math you can all do. You just got to practice it. But what we're going to essentially do is we're going to number our table. And so I'm going to number this like trial 1, 2, 3, 4, and 5. And what that's going to do is it's going to enable me to say, let's look at reaction 1. And it means look at only the things in this row. Reaction 2, only those things. And so we can then write things such as, what if we compare rate 1 to rate 2? What are we going to find? Okay, and so that might look something like this, where we've got our rate 1, which is right here, 12.5 times 10 to the negative 6 over 6.25 times 10 to the negative 6. And that equals, I'm going to kind of draw this so we can see, hey, this is what I'm creating. This general rate law is what we're going to use. So this is K times my concentration of I. I come over here to this column, and this is my concentration of I. And so in this expression is 0.080, and it's raised to the m. I don't know what it is yet. It's still unknown. Times the concentration of this, which we get from this column, 0.040 raised to the n. And these are all the values that were found in that first experimental row. Now I do the same for my number 2. So I'm going to use this value and this value. So 0.40 raised to the m, still don't know what that is, 0.040 raised to the n. All right, so this is where it gets fun. This can be put into our calculator, not a problem. The k's here, they're supposed to be the same k, so they cancel out. The n's, this right here, this is all the same on the top and the bottom, so they cancel out, which means I'm left with 0.080 raised to the m over 0.040 raised to the m equals this whole expression on this side. So what you do is, well, what I would do first is I would also notice that 10 to the negative 6 is on the top and the bottom too, so they're going to cancel. So I can rewrite this as 12.5 over 6.25 equals concentration of 0.80 raised to the m over 0.040 raised to the m. How does that help me? Remember those log rules? What happens when I take the log of both sides? Log and log. Well, this means all of this can be rewritten as 0.080 over 0.040 all raised to the m. And then when I take the log of this, then I have the log of 12.5 over 6.25 equals m log of 0.080 over 0.040. You're like, how does that help you? Okay, well, let's do some math. 12.5 divided by 6.25, that's equal to 2. 0.08 divided by 0.04, that's equal to 2. So essentially, we've got log of 2 divided by the log of 2 equals m. So what does m equal? M equals 1. So we just figured out that we can sub in 1 here into this equation. So now we figured out that our m is equal to 1. What does n equal? Well, what we can do next is we can compare another row. And so these two I compared first because I knew that 0.4 and 0.4 were the same, and so they're going to cancel in my algebra. Now I need to compare two equations or two experimental trials to cancel out in this row. And so which two are the same in this row? And that leaves me with 1 and 3. And so I need to compare these two in order to solve for n. And let's do that now and figure out what n is. So I'm going to kind of erase my ink marks. I figured out already that my m is 1. Now I need to solve for n. So let's compare the rate of 1 and 3. So rate of 1 over rate of 3 equals K times my concentration of iodine, 0.080 to the first, times 0.040 to the n, over K times 0.080 to the 1, 0.020 to the n. And so now my K's are canceling, my 0.080s are canceling. I'm left with this. My rate 1 is 12.5 times 10 to the negative 6. My rate 3 is 6.25 times 10 to the negative 6. My 10 to the negative 6's cancel. I am left with 0.040 over 0.020 raised to the n equals 12.5 over 6.25. All right, so now what do we do next? This is 2 raised to the n equals 2, therefore n equals 1. I could have also done the logarithm trick that we learned in the last slide. Either one works. So what that means is we know our rate equals our K times the concentration of iodide to the first, concentration of this raised to the first. And so this here is my final form for my general differential rate law. So that is all of that work just for part A. The second part says calculate the rate constant. That's my K. K equals my rate constant. So how might I do that? How might I find my rate constant? Okay, why not just plug it in for each trial? I know my rate, I know my I know this value, then I can solve for K. And you could do that for every single value. We're just going to do it for one trial. You could calculate it by yourself and find an average value. This one's pretty perfect. They all end up to be the exact same. That's what you get when you have textbook problems. They're not really real life very often. The odds of you running 6 trials and having the exact same K is pretty low. So let's do that together. So trial 1's rate is 12.5 times 10 to the negative 6 equals K, which is what we're solving for, times 0.080 to the first, times 0.040 to the first. Plug all that into your calculator, and you're going to solve, and you're going to get K equals 0.0039. But what are my units? Well, yes, you could go back to the prior slide and say, oh, hey, K equals my units are this. Or you could just use common sense to figure that out. What do I mean by that? Well, my rate is molarity per second. This is a second order reaction, which means we've got molarity to the first, molarity to the first. Therefore, my units for K are 1 over molarity times second. And so this is m minus 1, s minus 1. There is my final answer. Let's do another example like this. This is another differential rate law problem. We know this because we have our initial rates table given here. And notice this is just per minute. It doesn't matter if it's minutes per second. It's molarity per minute. That's still a change in concentration per time. This right here, all this is saying is we're establishing that the rate, the initial rate here, is dependent upon something that has a stoichiometric coefficient of 1. That's all it's saying. Okay. Besides that, once you establish that, these are initial rate tables. You can just simply determine the rate law by doing the algebra that we just worked. So let's do that. Let's compare our first and our second experiments. So I'm going to write my rate equals my K times my concentration of my first reactant raised to some variable times the concentration of my other reactant raised to some variable. So now rate 1 over rate 2. That's what I'm going to compare. And those equal 0.18 over 0.36 equals k times my NO, which is 0.1 raised to the m times 0.10 raised to the n, all that over k times 0.10 raised to the m, 0.20 raised to the n. So these to cancel, my k's cancel, and I'm left with 0.5, which is 0.18 divided by 0.36 equals 0.5 raised to the n. So n equals 1. And that's my first variable. Now we can go and do the next one. So far these have been pretty simple. We don't really need to do the logs. We can just do some easy math in our head. For this next one, we're going to need it. So n is equal to 1. Let's compare 2 and 3 now. So rate of 2 over rate of 3. That equals 0.36 over 1.45. You can see that's already not going to cancel out easily. So now we got 0.10 raised to the m times 0.20 raised to the first, all over k times 0.20 to the m, 0.20 to the first. My 0.20s are canceling and my k's are canceling. So if I plug 0.36 divided by 1.45 into my calculator, I end up with 0.24827. And that equals 0.5 raised to the m. You can see there's not a quick and easy way to do this kind of in your head. And so if we were to do that, we need to take the log of both sides. And so the log of 0.24827 equals m times the log of 0.5. So then the log of 0.24827 over the log of 0.5 equals m. Plug all this into your calculator and you end up with m equals 2. And so because of this, we can now determine our rate law. So m is equal to 2. And so my rate equals k times NO raised to the second, chlorine raised to the first. And this is my differential rate law. Now I need to calculate the value for the rate constant. So you can choose any trial. I'm just going to choose trial 1. And so if I'm just going to look at this one here, I've got my rate, which is 0.18 equals k times 0.1 squared times my chlorine, 0.1 to the first. And whenever I do that, I end up with k, and this is from trial 1, so I'll just give it a subscript, equals 180. If I were to do this for K2, I would get 180. And if I did this for K3, I would get 181.25. There's a little real life for you. Okay, but what about my units? Okay, you can't forget units. It matters. So what reaction order is this? This is third order. So you can't go back to the table because I didn't give it to you. Instead, you have to use your common sense. So remember, rate is molarity per second equals some constant here, and then we have m times m, and then m. So we have 3 m's on top. We need to only have one on top, so I need m squared on bottom, I need a second on bottom, and a 1. So if I use that, then my m's will cancel, and I'm left with molarity times second, which is what I want. And so my value for k equals 180.4, and it's actually molarity to the negative 2, because it was molarity squared on bottom, the negative just means it's on bottom, times, and I actually had a slight error here because my initial rate was minutes, and so that needs to be minutes, which means this one needs to be minutes, and so times minute negative 1. So there is my value for my rate constant. Don't forget those units. And so in this PowerPoint presentation, we have looked again at initial rates, and then we have looked at differential rate laws and practiced solving some of these rather complicated, but they're really kind of just mathematical puzzles that you can utilize to solve for these general forms of these differential rate laws and then solve for your average values for your rate constants. And so kind of look through these notes and see if you kind of understand the process for how to go about achieving these differential rate laws.